Good afternoon, everyone. I'm Dr. Anupriya, working as assistant professor in IIMT College of Engineering, Greater Noida. In this lecture, our discussion will be on UV visible spectroscopy, and the topic we are going to cover is basic introduction of spectroscopy, fundamental and instrumentation of UV visible spectroscopy, and their application of UV visible spectroscopy. When we consider spectroscopy, we have to understand what is the absorption and emission of electromagnetic radiation. Spectroscopy is a branch of science that deals with the study of interaction of matter with light or electromagnetic radiation. That means the sample where or matter interact with electromagnetic radiation, they change their energy via rotation, via translation, via electron transition, or vibration. The spectroscopy is the most powerful tools that record these changes of energy and give the information in the form of spectra. Before moving to the UV visible spectroscopy, we have to understand what is the electromagnetic radiation. Electromagnetic radiation is the flow of energy through space and medium with electromagnetic and electromagnetic field. And the packet of these energy known photon, and the energy of photon is equal to the h nu. Here nu is the frequency of radiation and hc upon lambda, here lambda is the wavelength of electromagnetic radiation. That means the energy of electromagnetic radiation is the function of frequency and wavelength. When we arrange the frequency and wavelength in increasing order of wavelength and decreasing order of frequency is called the electromagnetic spectrum. And the reason this visible light is the part of electromagnetic radiation which is visible to the human eyes, and the UV radiation is stand longer wavelength to the X-ray and shorter wavelength to the infrared region. In nanometer, the UV ultraviolet radiation has a range approx 200 nanometer to 400 nanometer, and the visible range is 400 nanometer to the 700 nanometer. Principle of the spectroscopy. Generally, the principle of spectroscopy based on the measurement of spectrum of a sample containing molecules of atom. That means the spectroscopy gives the information in the form of spectrum of energy change. And what is the spectrum? The spectrum is the graph of intensity of radiation versus lambda of radiation. And it's come in the form of like this. On the basis of interaction of matter with electromagnetic radiation, spectroscopy are two types: absorption spectroscopy and emission spectroscopy. In the absorption spectroscopy, the analytical technique which concern with the measurement of absorption of electromagnetic radiation. For example, UV visible spectroscopy, IS spectroscopy is the example of absorption spectroscopy. In emission spectroscopy, the analytical technique concerned with the emission of the particle or radiation is dispersed. That means is concerned with the dispersion of radiation. For example, mass spectroscopy is the example of emission spectroscopy. Now we will discuss how molecules interact with the electromagnetic radiation and change their energy. When molecules interact, they change their energy in the form of electronic, in the form of vibration, in the form of rotation, in the form of translation. The energy change by translation is very low, so it is negligible in the molecular spectroscopy. When we see the energy level diagram, here the R1, R2, R3 is the rotational level, V0 and V1 is the vibrational level, E1 and E2 is the electronic transition level. When molecules change their energy in the form of rotation, We can measure this energy change in the region of microwave and infrared radiation. When molecules change their energy in the form of vibration, we can measure in the IR region. When they change their energy in the form of electronic transition, we measure in the UV visible region. Absorption law. It is a very specific law that gives the information when a incident light, I know, pass through a sample containing the concentration C. Some part of incident light is absorbed by the sample and some part of the light transmitted. Now it is I. So that the absorbance of sample we can express as absorbance equal to epsilon Cf. Here, epsilon is the molecular absorptivity coefficient that give the information how much energy absorbed by the sample. C is the concentration of sample and L is the path length in which incident light is going to pass. Absorbance also we calculate in terms of transmittance because transmittance is the transmitted light divided by the incident light. And when we multiply with 100, we can calculate the percentage of transmittance. That means how much percent light is transmitted and how much percent of light is absorbed by sample. Now we are going to the UV visible spectroscopy. It is also known as electronic spectroscopy because the process of this spectroscopy work on the molecules absorb the light and get excited from excited state, ground state to the excited state. UV spectroscopy is generally concerned with the study of absorption of UV radiation. That means molecules absorb UV radiation, which range from 200 nanometer and the visible region is extended to the 400 to the 800 nanometer. In this technique, the valence electron absorb the light energy, thereby molecules undergo transition from ground state to the excited state. And this absorption is characteristic and depend on the nature of electron because molecules have two types of sigma and pi electron, so that the absorbance of the molecule also depends on the nature of electrons. Now we look on the instrumentation of UV visible spectroscopy. It has source of light which provide electromagnetic radiation, monochromator, sample compartment, detector, and recorder. In the instrumentation, when electromagnetic radiation pass through the monochromator, they generate a fixed particular wavelength. In UV visible spectroscopy, they generate approx 200 to 400 nanometer wavelength radiation. And this radiation, when passed through the reference and the sample, they record the energy changed by the sample in the form of spectrum. And this spectrum gives the information how much energy is absorbed by the sample. When matter interact with UV radiation, the electron present in molecules excite from ground state to the excited state. We know that molecules have bonding and anti-bonding molecular orbitals. Bonding have low energy and anti-bonding orbitals have high energy. So that electron move from low energy to high energy. So there are 5 possible transitions: sigma to sigma star transition, pi to pi star transition, non-bonding to sigma star transition, non-bonding to pi star transition, sigma to pi star transition, and pi to sigma star transition. First, sigma to sigma star transition. This type of transition undergoes in generally saturated compound because it has sigma bond. And this transition is high energy process, lie in the vacuum UV region. Electron from sigma orbital is extended to corresponding anti-bonding orbitals of sigma star. For example, methane have 4 sigma bond and can undergo sigma to sigma star transition, and so the absorbance maxima at 125 nanometer. Pi to pi star transition generally undergoes in the molecules have multiple bonds like alkenes, alkyne, carbonyl, nitrile. And alkene generally absorb in the region of 170 nanometer to 200 nanometer. In aliphatic ketone, the absorption mean around 185 due to the pi to pi transition of carbonyl group. And to pi star transition and is generally undergoes when a molecules have non-bonding electron. Compound containing double bond involving heteroatoms like CO, CN, and NO undergo such type of transition. And this type of transition requires minimum energy so that the absorption maxima is around 300 nanometer. Sigma to pi star transition and pi to sigma star transition are practically forbidden transition. Is not possible practical but only theoretical possible. And the order of energy sigma to sigma star transition has a higher energy compared to the other transition. Now terms used in UV visible spectroscopy. There are specific terms in use in UV visible spectroscopy. First is chromophore. It is a functional group that absorbs UV radiation and impart the color. For another definition, the functional group containing multiple bonds capable of absorbing radiation about 200 nanometer due to the non-bonding and pi to pi star transition. For example, nitro, carbonyls, cyano are the example of chromophore. And what is the exochrome? Exochrome individually does not absorb any UV radiation, but when they attach to the chromophore, they alter the absorption maxima and intensity of chromophore. For example, benzene have the lambda max at 255 nanometer. When they attach a phenol OH group at the benzene, the lambda max is reached approx 270 nanometer. When we attach aniline amine, the lambda max is 280. That means the OH and NH2 is a working as a oxochrome. When oxochrome attached to the chromophore, there are some specific terms used when they change the absorption and intensity. When absorption maxima of a compound shift to the longer wavelength, it is known as bathochromic shift. This effect is due to the presence of oxochrome or by change the solvent. For example, in alkaline medium, nitro paranitrophenol so the lambda max is 255 nanometer. But in alkaline medium, the lambda max is 265 nanometer. That means in alkaline medium, paranitrophenol so we saw the red shift and bathochromic shift. Histochromic shift when oxochrome shift the lambda max to the shorter wavelength. It is known as hypsochromic or blue shift. This effect due to the presence of a group that hinder the resonance or conjugation or by change of solvent. For example, aniline show the lambda max at 280 nanometer, but in acidic medium, generate benzenium chloride and the lambda max is 262. That means in acidic medium, aniline show the blue shift or hypsochromic shift. When we're talking about the intensity, if exochrome increase the intensity is called the hyperchromic shift, and if decrease the intensity is called the hypochromic shift. Here in the diene, oxochrome introduced so the increase the intensity in biphenyl when we introduce oxochrome, we decrease the intensity. Here the summary of the shift and effect. When oxochrome increase the lambda max is called the red shift, decrease the lambda max is called the blue shift. When increase the intensity is called the hyperchromic shift, if decrease is called the hypochromic shift. There are some factors which cause the lambda max shift. First is conjugation. The higher the extent of conjugation, the more is the bathochromic shift. Here, if we increase the conjugation, the band gap between HOMO and LUMO decrease, so that the energy decrease. We know that the energy inversely proportional to the wavelength. So that energy decrease, lambda max increase. So that on the to increase the conjugation, the molecules show the bathychromic shift. Hexachron. Now the hexachron exhibit bathychromacy by extending the conjugation. Here, phenol, the lone pair of oxygen, take part in the resonance and increase the lambda max. Similarly, the lone pair of nitrogen take part in the resonance and increase the lambda max. And so that the oxychrome show the bathychromic shift. Next is solvent effect. Solvent is most important part in the UV visible spectroscopy. Generally, the polar solvent stabilize the three molecular orbitals, non-bonding, pi bonding, and pi anti-bonding. When we, even if some molecules, so the transition from pi to pi star, if we use polar solvent, the pi star anti-bonding stabilize more compared to the pi bonding. That means the energy gap between pi to pi star decrease. So energy decrease, wavelength increase. That means if molecules we decode in polar solvent, the pi to pi transition decrease energy and so the bathychromic shift. When molecules with the n to pi star transition, the energy transition, and when we increase the polarity, the non-bonding stabilize more compared to the anti-bonding. So that the band gap between the energy gap between n to pi star increase. To increase the energy, decrease the wavelength. That means the lambda max shift to the blue shift. Means this transition so the high hypsochromic shift in polar solvent. The energy change non-bonding electrons show the higher energy change in the more polar solvent. Now here is a theoretical process to calculate the lambda max of conjugated diene and conjugated carbonyl compound. Here's an example of diene, and the base value of diene is 270 nanometer. If homoannular diene is 253 and heteroannular diene, the base value is 240 nanometer. There is a type of double bond present in the ring. If both of the bond present in same ring is called the endocyclic double bond. If different way is exocyclic double bond. And these are both the example of exocyclic double bond. Alkyl group of ring residue, carbon atom of the ring system or functional group connected to the carbon of conjugated diene. Here we can see that this is the conjugated diene and all the carbon is called the alkyl group of ring residue. Addition conjugated double bond. Look for the additional double bond which extend the conjugation of double bond. Here the two double bond and this the first is next is known as additional conjugated double bond. And this is the method stepwise to calculate the theoretical lambda max. Identify first the diene of specified. In the case of first of all we have to specify the diene. Next, calculate the number of ring residue. How much alkyl group is attached to the diene specified. Calculate the number of exocyclic double bond and calculate the number of additional conjugated double bond. There is some specific value we have to add in the base value of diene. For each additional conjugated double bond, we have to add 30 nanometer. For each exocyclic double bond, we have to add 5 nanometer. For each alkyl group, we have to add 5 nanometer and so on. For example, here we see the diene. So base value, this is the homoannular diene. So that the base value is 253. The ring residue alkyl group here is 6. This is the diene and the ring residue is 1, 2, 3, 4, 5 and 6. The ring residue 6 multiplied 5 nanometer equal to 30 nanometer. There is a exocyclic double bond. This one is the exocyclic double bond. So that we have to add 5 nanometer. Extended double bond. For the conjugation, this is the extended conjugated double bond. For the extended conjugation, we have to multiply with 30 nanometer. So overall, the calculated lambda max for this compound is 380 nanometer. Now, the application of UV visible spectroscopy, we can calculate the qualitative and quantitative analysis by Beer-Lambert law. The UV visible spectroscopy, we characterize aromatic compound and conjugated olefin, and we can calculate the number of conjugated diene. It can be used to find out the molar concentration. If we know the concentration of known, we can calculate the concentration of unknown solvent. Determination of impurities. If we want to check the solvent purity, we should take the UV visible spectra. If there is a additional peak in the spectrum, so that there is a impurity in the solvent. Detection of functional group. Every functional group have a fixed lambda max, so that it is easier to find out the functional group. Detection of isomer are possible by the UV visible spectrum. We can differentiate the isomer because in cis the bulky group, so the hindrance and exhibit the shorter wavelength compared to the trans because of the steric hindrance. And next, thank you for listening me. Thank you all.